So as you guess, I'm very happy to be invited by the organizer to give a talk here. It's in the tradition of all a series of meetings in kinetic equation where we are in presential. This time we are not, but hope for the future. And here's the title of my talk. It's a joint work with Nicolas Bess. I think he's among the people listening to that. It goes back to 2017. There was a meeting organized in Vienna by Norman Mauser, Uriel Frisch, and others about cosmology and Vlasov equation. And there was a guy who is well known in Vlasov equation, whose name is Pat Diamond in physics, and he claimed that recent work, by that time very recent, of Moore and Villani would contribute to the understanding of the, what he called the quasi-linear approximation. So what is the quasi-linear approximation? Quasi-linear approximation is on the next slide. You have the Vlasov equation that everyone knows. In particular, the electric field is defined in terms of the density of particle. I do that on the torus. So I have an equation which is the Vlasov. And then there's another equation which will describe the average quantity of particle, but it's an average which is done with respect to space. And so in some sense, it's a distribution of function in a torus or in a bounded domain that will describe the number of particles that do have the velocity v. And this was so, and I wrote this is a classical subject in plasma physics. I gave a reference in 1973, and it's still very active in plasma physics. It goes back, there's a complete journal, issue of the Journal of Plasma Physics devoted in 2018. Okay, very good. So I said I do it to the torus because what will help in the torus is that the advection flow is ergodic, it mixes everything in space. And I claim also it's a natural approximation whenever you want to look what is the behavior of the plasma in principle. And what you can do immediately is just to take the average with respect to x, and if you take the average with respect to x here, the advection term is gone, but then you have a term which you would like to identify, and that's all the subject of my talk. In some sense, it's what will be the flux. What I want to do is a kind of Fick law to define the flux in terms of what I can. Okay, and it's clear that this is not a trivial problem, of course, as we all know, because if you look at the kinetic equation, they will conserve a lot of things, in particular the L2 norm of the particle of the density. And if you look at the diffusion equation, this quantity decrease, the energy decrease, so you cannot expect to have a strong convergence from the first equation, solution of the first equation, to the solution of the second one. So the best you can hope is a weak convergence, unless the d of t, tv, the diffusion term, turns out to be zero. So, and it's not the first case where it's happened. This was common even in several talks of this meeting and before, where you go from irreversible dynamic to irreversible. And one of the standard trick is to use the Duhamel approximation. You factorize the advection term, you get the action of the advection at time zero plus the Duhamel term, and you can factorize the Duhamel term even more. So that's what we expect. Now, having that in mind, what I want to do, first I want to give you what will be a rescaled Vlasov and Liouville equation, because it's natural, it will be natural in some sense, and I want to try to see how it converges and why it may not converge, what are the main obstacles. Then at least there is a classical thing which goes back to Vasseur and the other co-worker, where they introduce some randomness, which is quite adapted to this problem. My contribution with Nicolas will be to say that it's well adapted to what we do and show that with some convenient randomness hypothesis, you get the Liouville equation, you get the quasi-linear approximation. So then I would like to compare with so these 2 points will be based on the introduction of randomness on the electric field. Now I would like to return to the genuine Vlasov equation, to the coupling, and show you what was done in the old time, going back to what Timon did, looking at some spectral analysis of the quasi-linear term, and all that will bring me to the conclusion, an open problem, to try to link these two different points of view. Okay, so far so good. So the first thing, I want a scaling, we are used to scaling, that will be compatible to the diffusion in V. So the scaling is that you have 1 over epsilon square, which will be in front of the collision usually, now is in front of the drift term, and then the electric field is just 1 over epsilon. And Nicolas, who knows more physics than me, said in some sense it's quite natural with the scaling of the physics. Now, if I just look at this formula, let's move the epsilon here, let epsilon go to 0, then I have the conservation of V grad F epsilon with the standard a priori estimate that we all know in this equation. This converges weakly to 0. That means that you have a weak convergence of F epsilon in this space. And if you have weak convergence in this space, at the limit, since you have on a torus, you end up with a function which is independent of x. It's the ergodicity of the classical flow on the torus. You will converge weakly to F epsilon of T and V. Well, that tells you that the electric field will be independent, the potential will be independent of V, and if it's independent of V periodic, that says that the electric field, always with no other hypothesis, will converge weakly to 0. That's the reason why I call it the baby version of the Landau damping. Now, to compare with the Landau damping, it's a good thing to keep in mind. You start with an initial data, which will be the profile which is independent of x, plus a perturbation, and you assume that all this business satisfied the standard Landau damping hypothesis. And if you would have that, you just copy the proof of Moreau-Villani, and you find out that the E epsilon of tau at time, which at the rescale time, will go to 0, not weakly, but strongly. So in some sense, I am after a situation, once again, where I have weak convergence to 0, not convergence to strongly to 0, because if it converges strongly to 0, the proof is done, but the diffusion is 0. Now, to go on and push on the understanding of this aspect, I want to make some more comment. So, I write the equation, and since I have average with respect to x, I have rescaled, I have the evolution of the density with respect to x, the average with respect to x, which is the gradient of the integral over the torus of E of x of t, f epsilon of txv over epsilon. And I take the weak limit of this quantity. Once again, I can just write this, the f of t using the Duhamel formula starting from the advection flow, insert it, put it in the equation, make a change of variable because I had the 1 over epsilon square in front of v, and I end up for this quantity, which I circle in red, which is the flux. This flux will be given by the integral over dv dx, and the integral from 0 to epsilon t, or let's say that will be the integral over dx, of the integral from 0 to t over epsilon square. It's just a change of variable, and I test it since I expect weak convergence. I test it again, a function which just depends on v, and then I obtain, since I put the test function, the integral with respect to v, this quantity, which is the flux, and this again, and what makes appear the gradient of E of x, term in blue, t minus epsilon squared sigma x, epsilon x plus sigma v. So you see, you have the f, which is oscillate, and then you have a tensor which appears here, and and I will comment on that on the next slide. Hopefully, what I expect, if things will work, is that the diffusion term will be the weak limit of this tensor. And this tensor, in this present field, which I could call plasma turbulence, it plays a role, the same role as the Reynolds stress tensor in the fluid mechanics, where you have some turbulence and you want to look at what is the limit of the fluid thermodynamics. It looks also in many other aspects of weak turbulence. So having this formula, and as it appears in the previous equation, brings to two questions. First, if you apply two test functions, how this will converge to a term, what will be the limit of the diffusion term, which will appear here, and how it looks like, will it be non-generate, will be non-singular? So that's the first question. And the second question, if you go back to all the equation, it's a question about decorrelation. Can you, at the limit, write the Fick law, the flux, at the limit as the weak limit, the product of the weak limit of the density of particle against the weak limit of the stress tensor. So you have two questions, identification of this quantity, and then the second is the weak limit. Now there is a very simple computation to do. If you want to stick to the Vlasov equation, you know that you get the electric field in terms of the potential. So you get some extra regularity in space. So, and you are looking for weak convergence. Weak convergence cannot come from weakness, from oscillation in X. They will come from oscillation in time. And it's in agreement with what you observe in physics, where you assume that the field will oscillate faster, like omega frequency over epsilon square. So assume, write the thing in Fourier space, that the phi epsilon can be written as the Fourier component of the potential can be written as something which is some rather smooth in K, control, and then an oscillating factor. Put it in the formula, turn the crank, and you end up with, for the diffusion, to this quantity. And this quantity, you have a T over epsilon square. and the sinus omega k minus kv of t over epsilon square divided by omega of k minus kv, this goes to a delta mass at the point omega k, at the point characterized by omega k minus kv equals 0. So you end up, if you could take the limit of the Fourier component of the potential modulo an oscillating term to this expression, which is the sum of phi epsilon k square that multiply tensor k grad v, and it's integrate over omega k over kv minus omega k. So that's means that you just integrate a delta function, again test function, on a set which will depend on the distribution of the frequency omega k. Basically, if you just use the a priori estimate, that it says that that at the limit you will have a function in L2 or L1, a measure, not a measure, that would say that this quantity at the limit is 0. Otherwise, if it really a good, it may work, but this depends really the way the omega k behave. Since it really depends the way the omega k behave, it's a natural idea to look at the stochastic approach of the problem. So I just move from the definition of the electric field by the Poisson equation to a situation where the electric field will be a random variable and will be tailored, will be modeled in the spirit of the consideration that I made just before. Now, to do that, since a random variable, I assume that the total expectation is 0. I assume that I have a finite time decorrelation at the order of epsilon. So if t minus s is greater than tau time epsilon square, then the expectation of E epsilon of t and x at A epsilon of s and y, this quantity is 0. And I assume, make an hypothesis about what's happened when t minus s is less than tau epsilon square. Basically, that if I write the thing in terms of Fourier, I assume that it's a Fourier component of the field with the same oscillation, same weight, omega k over epsilon square, let's say the t over epsilon square, which is the scaling that I had before. Okay, if I do that, and I look at the Fourier component of the potential, and I make the hypothesis that the expectation of the scalar product of the Fourier coefficient of the potential at k and k prime will be 0 when k is different from k prime, and that the expected when k is equal to k prime, it's given by a function which depends just on the modulus of t minus s over epsilon square. And I make some hypothesis about the regularity of this guy, which is in agreement with what you will know about the Vlasov equation. Now, when you have written this formula, it's even, you take the Fourier transform of the A k of sigma, you introduce this function, which is the Fourier transform of the correlation function for any mode, and by very classical theorem, which is Palais-Wiener, it will say that the Fourier transform A k of s is analytic, and the other thing is that it's also non-negative, because this quadratic form will give something which is non-negative, and you just apply the Bochner theorem for that. So that with this idea, you write the diffusion matrix, and bingo, you find that it is something which is positive, non-degenerate. The next point is to take care about the finite time decorrelation, and at this point in this spirit, I will just borrow on what was done by Vasseur, Poupeau, and other people of this time, I just try to look at the finite time decorrelation, and I find out that with the hypothesis, the space of homogeneity, so that will be the diffusion coefficient, and I find out a proposition, which is that if I look at not the limit of just the E epsilon, F epsilon over epsilon, but the limit of the expectation, since the two electric fields do not interact when T minus S is greater than epsilon squared tau. Here I can move into the Duhamel formula and make appear the expectation at the time T minus 2 epsilon squared tau, and the expectation for the function, and the expectation for the tensor at the time T minus epsilon square, which is exactly the thing I want. And there is a reminder. The reminder will go to 0 because I just use for that the property of the regularity in space. So then I can take the limit in this quantity, and the theorem which will obtain at this level is that I will have, under the stochastic hypothesis, I will have a diffusion coefficient which I can completely compute in terms of the hypothesis on the randomness. I will have at the limit, the weak limit of the solution will converge to the solution of the quasi-linear approximation, because with the decorrelation, I can take the limit in the equation, in the drift term, and I have identified this D of V as something which has the right property. And so here the solution is unique. At the limit, it's not only it's not a subsequence, but all the solutions which converge. And the average, if you look at the average, you work a little more, you can get a strong convergence. So it's a really natural result using the randomness. Okay. And then I can make some comment to introduce, in some sense, the rest of my talk, which will be a link between this approach, I try to make a link, and what was done in the old time, and compare with experiment. So, the first comment I said, at the beginning, I insist that this is deriving a diffusion equation from an Hamiltonian system is really something very classical, and it's a problem we have all been working. We have many people in mind about that. And but what is known is that you need just weak convergence, and more or less the randomness is always compulsory. The other thing is that the analysis has to be made rather on the solution than on the equation. You really need to analyze the weak convergence of the solution. And then, when then one of the basic tools is the use of the Duhamel series that goes back to Hennenfent, Erdős and others. And then, if I look back at the paper that we use, the main aspect that we use to connect it with what experiment shows is that it's enough in the Duhamel series to go back to the second iteration of the Duhamel series. And this, in some sense, is a closure relation in the sense of propagation of chaos, saying that it's enough to go to the second iteration of the Duhamel series. Okay, so that's where I am for this kind of thing. Now I want to return to the case where the electric field is not random, but is really given by the Poisson equation. And I have all the conservation of the Vlasov equation, assume that the initial data is smooth, and I have the classical result that do exist in particle summer due to Benoit about how regular maybe the electric field over the time, which is 16. Now, I want the other thing which is in the literature, which I want to comment and try to interpret in a modern way, is to prove the validity or the good reason for a short time approximation of the Vlasov equation by the diffusion equation, and producing also a coefficient of this diffusion equation, and try to give an interpretation that will in some sense be adapted to the first part of my talk. So I start with a profile, write the solution as a profile G of T and V, which will be under perturbation, and assume that the average of the perturbation of the torus is equal to 0. That you can always do. And that the basic profile, which depends on time, which is independent of x, is of total density in V equal to 1. Now, if I insert this ansatz in the Vlasov equation, I obtain two equations. The first, and I have put an epsilon here, so the epsilon reappears here. So I have d over dt of epsilon squared gradient of V plus the gradient of V of E epsilon of H. The E of H refer to the fact that the electric field is computed in terms of the perturbation by the Poisson equation, and this is what is written here on the right-hand side. So I end up with this equation, and what I use is the fact that I have an epsilon square here. So I have an epsilon square here, and since I have an epsilon square, I want to analyze the equation for the perturbation. Perturbation gives dt of V grad x plus A of H grad V is equal to E epsilon grad V of the E of H minus the average of E of H integrate over x. So that's, I will replace the equation, and the main observation is here I have an epsilon square, and I will show you that I can construct solutions which are very natural, for which I can replace the epsilon square, so on the right-hand side, by an epsilon 3. So all the process is gaining one factor in the dependence with epsilon, going from epsilon square to epsilon 3 at the power 3. So I do that. Since the process is very sensitive, I don't do that for any solution, but I will start with a special class of initial data. Special class of initial data is to try to start from a G0 of V and start with an epsilon A of 0 and K, the gradient with respect to V of G0 of V multiplied by A epsilon X, and divide by lambda 0 plus A key V. Now, I want, in the next slide, I will tell you what is the lambda of 0, which is essential in the construction. And from that, I will construct an approximate solution, which is G of T of V, which is the profile which was on the previous slide, plus epsilon time, the same thing as what is here, except the lambda 0 has been changed in a lambda of t plus ikv, and I have an amplification factor, which is the integral from 0 in t, and it will be the real part, there's typo, of lambda s. So we want to move from here to there, tell you what is this quantity, and tell you what is the lambda of t. There may be people familiar with this construction have already guessed, but anyway, it's on my next slide. On my next slide, I start from the lambda 0, and the lambda, and given the G of 0 and V, I define the lambda 0 and the K such that this equation, which I call 22, be satisfied. This is exactly what the equation which was introduced or popularized by Penrose. Whether there will be solution of this equation with a lambda 0 partial of lambda 0 positive will govern the stability or the instability of the linearized problem. Now, let's do that for G of 0 of V. Now, if I make the assumption that and I know by the spectral theory of the linearized transport equation that under this assumption, party real of lambda positive, there will be for party real of lambda greater than certain lambda, a finite number of eigenvalue of the transport equation, and this eigenvalue, their real part will be bounded for, and there will be a finite number. They will be simple eigenvalue. I assume that in this situation I have one. The eigenvalue is simple, and I know that as long as the Vlasov equation has a smooth solution, one can prove the analyticity of the solution of the Vlasov equation. I think that was a series of paper of Ben Ashur. So I assume by standard spectral theory that if lambda 0 is simple, lambda of t is analytic, and then I can put, and since d over d of gt is of the order of epsilon square, if I take the derivative of lambda of t, if I take the derivative of lambda t, if I derive this equation, what will appear is the derivative of g of t. That will say that the variation of lambda t is of the order of epsilon square. Now, if I put this observation together in what I have presented before, I end up with the fact that the difference between h and this ansatz will produce an error which is of the order of epsilon 3. And this is the conclusion which I will have here. I start from R of 0 of x v, and I construct the ansatz for this case, and then I put all that in the equation, and I will find that instead of having an O of epsilon square, if I just add the simple decomposition, I have gained a factor, a power 1 from epsilon 2 to epsilon 3. And this is the situation which I get in this problem. I'm almost finished. And of course, then I have a series of remarks on this construction. The first, of course, was the consideration of unstable eigenvalue of the linearized operator near 0. Then, of course, you can extend the formula to any finite number of eigenvalue. You observe the fact that if you have an eigenvalue lambda for mode k, frequency mode, then the conjugate of lambda is an eigenvalue associated to minus to the frequency minus k. So you can couple the real part of these two eigenvalues together and construct a solution for a family of solutions for which you can write for the average, g of t of v, you can write g of t, you have the factor epsilon square, you have a diffusion coefficient, which is exactly the type of thing you find in physics book, and there is an epsilon, instead of having an epsilon square, you have an epsilon 3. So I have in some sense told the story in the language of functional analysis, but it's more or less the story you find in the old book of physics. Now, when you have that, you work a little more, use the fact that all this error can be controlled by using the analyticity of the initial data, and they are valid for a finite time, and in fact you can add, as long as you have a good dependence on lambda of t, if the initial use the analyticity, you can move from epsilon 3 to epsilon 4 to any power of epsilon, but just for a finite time and for a family of initial data well defined. Well, that's more or less what I want to say. I would like to make a series of comments on this program. Okay, so the first comment is that this computation, which I have shown to you, they had been done by linearizing looking at the linearized problem near the profile, near t equals 0. Now, the lambda of t, they correspond to the pure point spectra. Now, you can think about the thesis of Pierre de Grand, where he described not only the eigenvalue, then but when you have the eigenvalue, then in the spirit of scattering, you can extend the resolvent to the negative half-plane R of lambda, and you obtain the pole of the extension. They are exactly what you find in scattering theory, which are called resonancy. And if you look at the interpretation in physics book, what corresponds to the eigenvalue, they are called particle, and what corresponds to the resonancy, they call it wave. Now, if I return to the Moore-Villani-Moore, or any proof of Landau damping, you find out that the proof is, so the situation what they consider is the case where you have no Penrose unstable mode. You just have resonancy. And in some sense, if I go back to the physics, it's what the next step is to look at what will be the interaction between resonancy wave and particle. There are some poetic words in physics literature where the particle glide on wave like people doing surf, but I leave it to you. And but in a way that says that for short time, as long as you have eigenvalue, this term, which is a diffusion, smooth the thing, so it making more and less, the profile becomes more and less smooth, and then if it's too smooth, then the profile is monotonic. If it's monotonic, there is no more point spectrum, and then what's become dominant is the interaction of wave. And then that turns out to be like at the end, after this short time, it becomes to be something which will be like the Landau damping. And it's exactly what you find also in numerical configuration. And I can just illustrate by two pictures for that. The first, the eigenvalue are here. There's 2 minutes. They are here. And then they move here, and at the end, when the eigenvalue disappear in the imaginary axe, then what turns out to be dominant are the resonancy. Okay, and it's exactly to introduce the validity of the average. I just show a picture done by Nicolas, where the bump in tail appears as an average, really, of numerical computation. Well, final remark. The goal really of this story is to produce a V-dependent equation. Now, when I start to look at the whole time, I start to look to the Boltzmann equation or neutron transport. There were comments about the computation of the homogeneous equation, independent of x, and in my spirit, it was, in some sense, related to as a tool to compute all the problem by fractional method. First you do the advection, then you do the Boltzmann homogeneous, and so on. But what comes from my talk and all this literature is that it may be important, more important to, or also important to look at situations where you get directly an equation for the evolution in V. And that exists already in the literature. There is at least one case where it's done in our language, and this will be the Fokker-Planck, which if you start from the Fokker-Planck, you average in X, you will get this equation. Getting it directly, that can be found, or at least recently, in paper of Deriving, Saint-Raymond, which is a very nice result. And they have a Cirm average, so just to make a slight philosophical comment, you need, in all the first part of my talk, there was average. Here you obtain directly an equation, but in some sense, even there is an average because the other part of that construction is what they call the pruning of the tree. So pruning of the tree means refer to the dynamic, which has a reasonable number of interaction, which is to be the nice one. So in some sense, it's an average with respect to all the scenario. So that means that there is some similarity between averaging over all the different dynamics or putting beforehand some randomness to get something that we can see. Okay, thank you very much for your attention.
Okay, thank you very much, Claude.
That's it on time,
yeah,
I guess.
Okay. So there are some question or comment? Any comments? You can ask your question by chat also.
I have a stupid question, Claude. I already asked question to Claude. Is there any chance to do that for other equations that Vlasov?
I mean, it's that should be okay. Let's say in turbulence theory, people deconstruct equation for the profile. Let's say the profile. Let's say if you look at the equation of weak turbulence for Schrödinger equation derived for Schrödinger we use for water wave, you start from equation where you have a dependence on X, a dependence on K, on the frequency, and at the end of the day, you get exactly a profile on K. Mm-hmm. So it's exactly, in some sense, this model is trying to go directly from something which depends on X and V to be described by something which just depends on the velocity or the frequency. So I think it's not only of course, the example of the Fokker-Planck, it's not only for Vlasov, but I think it has much in common with many other problems where the introduction of randomness, irreversibility will bring to something which is not only an equation which doesn't depend on the velocity, but which is average on all the space, provided it's in a bounded domain or that you want to look what's happened in a small part of the domain. No, I think it's here I try to put things together, several ideas, but I think it's a general problem for our community.
Okay, thank you.
Okay, you have also a question by Pierre. You can read it on the chat, or I can also ask you the question if you want. You can read it.
A question by Pierre. I don't see a question by.
Okay.
Oh, yeah.
He says, what can you do? What can you do in the non-periodic case?
Okay, non-periodic case. The first thing. If you give me the mathematics, I can do it. The first thing is to. First thing is to have the ergodicity. The ergodicity you have for free, or maybe it's already done if you assume that the particle, when they hit the boundary, they just are affected the trajectory by specular reflection. So you look at a BR ball, which and when the ball hit the boundary, they reflect by specular reflection. Now there are some domain where it is proven, and that goes back and also for maybe others that then the flow, like in the torus, is ergodic. In the torus, you can do that by Fourier transform, but this is true in some domain. So that gives you the weak convergence with the scaling to something which is independent of X. But it's only nice. But then the rest of the program needs much more, which in this language of dynamical system is referred to the mixing property. And I don't know how this could be simply done in this situation. There are maybe situations where it could be done, but okay.
I have also maybe one question or two. Do you think that you can make your analysis, at least for the first part, your analysis on the characteristics instead of working on the kinetic equation on the distribution function? Maybe the analysis can work also on the characteristics, no?
Characteristics, Victor, what do you mean by characteristics?
The characteristic of the transport equation. I mean, just follow the trajectories.
Yeah, but I use the in the first part, everywhere I use the trajectory. I use it because the trajectory is the base of the Duhamel formula.
It's okay, it's the same, okay.
It appears there. It's the base of the fact that it converges weakly on the torus, or as I said, to something which is independent with the scaling, independent of X, but depending on V. So that's also a point. Okay. And then even in the last part, which relies on the eigenvalue of the Penrose, and what Pierre, by the way, did in his thesis, is you look at the spectral theory for V grad X plus a perturbation, which that means that the vector field is independent. Maybe on some other geometry, what could take a vector field which depends on X, but that's another story, X and B, but that's another story.
Okay. Is it important that the potential is Colombian, or you can do it also for gravitational, for Newtonian potential?
I don't know what is I know. I use the potential just really in the second part where I use the Penrose construction and the rest of the analysis. I don't see for the spectral theory, you don't need a sign on the potential. What you need is to have to control the regularity of the solution in the spirit of Benoit and Pierre-Louis and other of the Vlasov equation. Because I use the space all these businesses using the spatial regularity in X with oscillation in time, which combine the two things, whatever you do in this business.
So I just have seen that Nicolas Bess has answered also that it works in the gravitational framework. Sorry. Okay.
Yeah, Nicolas must be right. Yeah, but I don't know what are the theorem about the regularity of Vlasov Poisson in the gravitational. In more than 3 dimensions there are singularity.
Yes.
Yeah.
Yeah, in 3 dimensions.
In the gravitational case for Vlasov Poisson.
Yeah. Yeah, it's okay for the gravitational. For 3D, it's okay.
For 3D, it's okay. Yeah.
But yeah, for 4D, it's not well posed.
But yeah.
Close up, but it's okay.